Okay, welcome back. This is now 7.2, and we're looking at kind of applications of the integral. And in this case, we're actually going to be venturing into 3 dimensions, which is kind of a new thing. And we can do that by sort of reinterpreting the integral as an accumulation of volumes as opposed to accumulation of areas. Okay, so it just takes a bit of creativity on our part, but we will get there. Okay, so here we go. Beginning now with these notes. Integration as accumulation. Okay, so recall sort of our construction of the Riemann sum in chapter 5. So we can use the Riemann sum to get an approximation for the area underneath the curve. Ugh, that was a terrible curve. Let me redraw that. So something like this is our curve, called f of x. And we're going from some point A to some point B. So the Riemann sum will add up a bunch of areas of rectangles. So maybe we have some rectangles here, and dot, 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 and some sort of arbitrary rectangle right here, and then dot, 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 all the way to the end. Okay. And, our goal is to get the area underneath that curve. So what we did was kind of, take a look at this one particular, I got a little too carried away with my curve. Oh, okay. So this particular guy, we want the formula for the area of that guy. If its location is at point x sub I, and the width of the rectangle is change in x, the area of that particular rectangle will be base times height, right? Or height times base, written in that way, is f of x sub I times change in x, right? And then the idea of accumulation is basically you have, and I've already introduced my Riemann man in the last section, you have this guy running across the x-axis in this direction, and he's accumulating all these areas, and that gives you an approximation for the area. And then if you take the limit of that, you get our nice integral. Okay, so ultimately it'll be a limit of the sum of the a sub I, which will give us our usual integral from a to the b of f of x dx. Okay, so that in a nutshell, is all of chapter 5.2, 5.3. Okay, so now what we're going to do is kind of reimagine this a sub I as actually representing kind of a volume. Okay, its picture will be that of a. I'm going to have to extend the picture a little bit now, because what we're going to be doing is rotating that region about the x-axis. Okay, so we're going to use the same kind of curve here. We'll just use f of x again. So it drops down and then it goes back up. Okay, so there's our f of x. And it's the same region that we're working with. So going from some point A to some point B. And the kind of construction of rectangles, it's exactly the same. And then we'll have one arbitrary rectangle here at location x sub I with width change in x. Okay, and on until you get to the last couple rectangles. But in this case now, the rectangles don't represent area. We're not going to think of them in terms of areas. And instead, we're going to think of them as indicating a volume. Okay, and the volume of what? What is this thing? It's going to be kind of a cross section. Okay, so what is it? What are we trying to do? Maybe it's a better question. We're trying to find the volume of the object that's generated by rotating that region around the x-axis. Okay, so if you've ever worked like in a shop on a lathe, something like that, you know you kind of rotate this thing around really quick. But if you rotated that region around, what would you end up with? You would end up with kind of a goblet type object. So you would end up with something like this, right? And then maybe what we're after is finding the volume of that thing that's made by rotating this region about the x-axis. Okay, so what I said, we're going to sort of re-envision these rectangles. So imagine me just taking this one particular rectangle, and I'm going to have to edit my little picture over here in order to pull this off. I'm taking this one rectangle, and it represents kind of a cross-section of this disk. As I say, the book will say disk, but it's really just a smushed cylinder, so a really short cylinder. Like if you took like a pop can and smushed it down, that's what they mean by disk. It's not necessarily a flat disk. Okay? It's more of a flat cylinder type thing. Okay? And then you're in 3 dimensions now, so we can kind of add in this extra axis. Okay? As opposed to just the x and y axes. Okay, so let me maybe kind of put that in red, and then over here, where is it? It's inside this guy. And sort of the dimensions on that rectangle will allow us to figure out a volume for this particular disk. Okay? So if we took this disk, and it may be better if we lay it flat in order to kind of put it in terms of a cylinder, because we know the formula of a cylinder. It's pi r squared h. Okay, so I'm just taking that object and laying it flat. What are the dimensions of this thing? So in order to get this v sub I formula, I need to know the radius, and then I need to know the height. Okay? So the radius is going to be from the middle all the way to the edge of the circle, right? So this distance right here. And that distance right there is just the height of that red rectangle on the picture. So you can get that then by just evaluating f of x sub I, right? So that radius, I don't think I have room to kind of smush it in there, f of x sub I, okay? And of course that is then the radius that we need for our volume formula. Okay? So I can kind of go back to my v sub I formula and rewrite it as pi times the radius squared will be f of x sub I squared. And then finally the height of this cylinder, and that's going to be this dimension right here. And what is that dimension? Well, that's the base of that red rectangle, right? So I can even kind of draw the rectangle in here. Okay. And yeah, I guess I should have kind of connected the thingamajig. So it should be more like it's over here, right? Okay, so I need the length of the base of the rectangle, which in our case is given by the change in x. So this height dimension, which is kind of like a base of the disk, is going to just be change in x. Okay, so that will be the height of the cylinder. So usually you're trained to kind of think of cylinders like a pop can, but what we're saying here is to smush that cylinder down, and that will be what we're calling the disks. So the h value then is change in x, and then we just send our Riemann man across to collect. Now instead of areas, he's going to be collecting up these volumes. Okay, so these v sub I values. So before he was collecting a sub i's. So we'll smush that in there. Okay, now he collects v sub i's. Okay, and if you go through and collect all those v sub i's, you get pretty much a pretty good approximation to the figure. You're going to, again, we can kind of get an idea of what it looks like. So this would, let's draw kind of the top of the curve. Whoops, that's not very good, but you know, you're kind of getting approximations for the cylinder there, and then you have a cylinder here. We're really going to test my artistic skills today. And then maybe another cylinder here. And then the cylinders kind of get smaller. And it's all depending on, you know, the shape of the curve. I guess I butchered the shape there. Yes, glad I did not major in art. So something like that is what you're kind of getting in the end. So this would be kind of, you know, your Riemann man is running in this direction and accumulating all of these volumes in this bag. Okay, so you'd end up with this sum of these v sub i's, and then you take the limit of it as the number of those volumes, number of those disks go to infinity, and you're gonna, you know, we can fill in the blanks here a little bit. So, you know, what is it? It's pi r squared h, so pi times f of x of I squared h, and that becomes the Riemann sum, and we could take, you know, the limit of it, and we will get our integral, factor the pi out of the formula, and you end up with this as kind of the formula of the day, okay, for determining the volume of a region rotated about the x-axis. Great, so let's go ahead and try some applications. We're going to be doing rotations about the x-axis, rotations about then the y-axis, and then we'll also do non-axis rotations. Okay. Then we'll also have the washer method, which basically allows you to find volumes of, excuse me, objects that have holes in them. So, you know, you'll want to find the volume of maybe a ball bearing with a hole drilled through the middle of it. This will allow you to do that. Okay, so anyways, let's take a look at some examples. So the first one, we want to rotate a region about the x-axis. And in particular, they give you the formula for the region, the formulas for the region. Okay, so the line negative x plus 1 has a y-intercept at 1, and then it goes down 1 over 1, so it should be right here. The line x equals 0 is the y-axis, the line y equals 0 is the y-axis, so we're going to end up having to rotate this region about the x-axis. We indicate that with a little loop like that. The end result then will be what they call an elliptic cone in Calc 2. Calc 3, you'll look a little bit more in detail at these, what are called quadric surfaces. And there's, you know, there's particular types of these things, but anyways, in this case it's an elliptic cone. Right, so we want to find the volume of that elliptic cone, and something that helps me, because things are going to start getting real crazy real soon. I like to draw the little running guy, and I also like to draw my rectangle, which represents kind of that cross section of part of my disk. Right, so if I were to rotate that little red thing around the x-axis, you would end up getting your disk looking something like this, where your red rectangle is right here. Okay, so the formula, you know, is pi r squared h, basically. You can factor out the pi. The radius is variable as the Riemann man is running across. The radius of these disks is variable. So to get the heights of those disks, you need to use the formula for that particular line right there, the negative x plus 1. And it'll be squared, and then times height, which is just dx. And it looks like we're going from 0 to 1 on the x-axis. Okay. Yeah, that's pretty much it. Then you just have to integrate the thing. So you get pi. We're going to have to FOIL this, x squared minus 2x plus 1 dx from 0 to 1. Get the antiderivative. So x cubed over 3 minus 2x squared over 2 is just x squared plus x from 0 to 1. And then you get pi times 1/3 minus 1, which is the same as 3/3. Well, we don't even have to go that far, right? Plus 1, which is another 3/3. So it's just going to be 1/3 minus, plug 0 into all those, you're just going to get 0. So it's going to be 1/3 pi when all is said and done, is as the volume of that elliptic cone. Okay, let's look at another. So this time we want to rotate y equals square root of x, y equals 0, x equals 3, about the x-axis. Okay, so get a picture of the region that we're working with. Square root of x, of course, 1, 2, 3, 4. At 1, it's at 1. At 0, it's at 0. At 4, it'll be 2. Just doing some point plotting. And then kind of get a picture. Y equals 0 is the x-axis. X equals 3 is a vertical line going through 3. So the region we're rotating is that region, and we're going again about the x-axis. The end picture, and of course you don't have to draw these pictures out, but I think maybe sometimes it's a little helpful, is this thing. Okay. And it's called an elliptic paraboloid because it kind of has a parabolic shape. If you do a cross section straight through the object, and then if you do an up and down cross section, it's a circle or an ellipse. So they call it an elliptic paraboloid. But you don't need to know that. Okay, so anyways, we need to get the volume of that thing. And again, you know, I like, and you may not necessarily care, but just find some way to kind of keep things in order. So the Riemann man is going to be running across, picking up all these volumes based on these red rectangles, which will be variable in height. In other words, the radius is variable, and the radius is given by the square root function, okay, the height of this rectangle. So our formula then, pi times the radius squared, so square root of x squared, dx, and let's say we're going from 0 to 3, picking up all those disks. So we'll end up with pi times the integral of x dx, and then just integrate, so pi x squared over 2 from 0 to 3. At least we're going to get 9/2 pi when all is said and done. For the volume. Okay, so kind of, you know, at this point, kind of so simple. We want to, of course, make it a little more complicated to handle more and more scenarios. The first sort of complication is the vertical revolutions. So horizontal, or let's say what it is. X-axis rotation versus the y-axis rotation. And the only real deal is that kind of the orientation of your Riemann man is going to be different, right? So for the x-axis rotations, your Riemann man is collecting volumes going in that direction, okay, some of the volumes. So again, if you had, like the previous example, some region like this, and you're rotating it about the x-axis, your formula will be for the radius will be in terms of x. So you're dealing with the limit of the sum of pi r squared h's. So if this function is f of x, you have your f of x sub I, this particular x sub I, and then you have a change in x here, squared times change in x, and that gives you the integral of the day. So f of x squared dx. Okay, so now the orientation will change, and if we're going about, say, the instead now the y-axis, you would have your running man going like this. Okay. Put those little, summing up volumes, trying to draw that sideways. Right, so the first thing we're going to need is this function in terms of y. So instead of f of x, we'll have some sort of g of y region that we're rotating. Let me get the rectangle. So now the rectangle will be kind of horizontally oriented, I guess is the way that they kind of talk about it. Regardless, the rectangles always be perpendicular to the axis of rotation. Okay, so here we're gonna now, instead of x sub I, we'll have y sub I, and then you'll have your change in y, and the formula for the end integral will be the limit of the sum of these v sub i's, which in this case will be pi times g of y sub I squared times change in y. And then if you do that limit, you'll end up with your new integral, pi integral of g of y dy, g of y squared dy. Okay, so one thing, I've noted a couple things here, but the main thing that I kind of noted in my notes to remind you of was the rectangles for this method for discs or washers, because it's going to change once we get to the next method in the next section, what's called the shell method. But right now, the rectangle for the disc and the washer is perpendicular to the axis of rotation. Okay. Later on, when we deal with the shell method, you'll see the rectangles are parallel. So for shell, everything's parallel. Okay. So let's look at an example of vertically, or the y-axis rotation. So they give you y equals x to the 2/3, which is basically kind of like a square root type thing in the end. Let me draw it. It's concave downwards on this interval, and the book gives you a picture this time, so they don't just, if you want the other formulas, there's going to be one at y equals 1, and x equals, I guess what would x equal? X equals 0. So first off, the x to the 2/3 looks like this, from 0 to 1. Okay, y equals 1 is this parallel line, horizontal line parallel to the x-axis, and then x equals 0 is just the y-axis. So the region we're rotating is this upper region here, and we're going about the y-axis. Okay, so I should note that somewhere, y-axis rotation. Okay, so the rectangles are going to be located like right here, and the running man, of course, is going up the flagpole. Make sure he's going kind of the right way. this. Right? And accumulating those volumes. Okay? So this time, the heights of those rectangles are based on the y value. In other words, we need a formula in terms of y for that curve. And then, of course, the width is changing y. Okay, so our formula for the volumes, in this case, I need some g of y sub I squared, and of course I need a pi, and then I need my change in y. And that little red, rectangle then will represent one little disk in my accumulation of disks. Okay, so where is that red rectangle? It's in here. And then, of course, the object that we're looking at is kind of a horn shape. Don't have a neat name for this guy, but it's going to look something like this at the end of the day. Okay, right, so what did I say? I need this formula in terms of y, and right now it's in terms of x. So that's an easy fix. You're just going to raise both sides to the 3/2 power, and you'll end up with x equals y to the 3/2. And that will be the formula that gives you the heights of those particular rectangles, and then allows you to figure out the volume of the disk, and then you just add them all up in our integral. So you'll have pi integral of y to the 3/2 squared dy, and it looks like we're going from 0 to 1 on the y-axis. Our running man is going from 0 to 1. Okay, so let's go ahead and evaluate that. So this looks like pi y to the 3/2 squared. You just multiply the exponents, so you just y cubed dy. Then that'll equal pi times y to the 4th over 4. And we want to evaluate from 0 to 1. So when all is said and done, it's just pi over 4 for the volume of that guy there. All right, so I think that's kind of the idea. You think of this f of x function as kind of a radius function. Okay, so when you go to your formula, you kind of think of it in terms of big R of x dx, where the f of x, is the r of x. So this f of x is thought of as a radius function, the radius of the disks. Okay, and then over here on the other side, it's got to be in terms of y. Again, this r of y then, in this case, is the g of y, which again just represents the radius of these disks. Okay, so a lot of times if it starts getting more and more complicated, you kind of want to say, okay, this is my r, this is that, and sometimes that helps. So I'm just kind of trying to think ahead a little bit. Anyways, you have x-axis rotation, y-axis rotation. You can also have non-axis rotations, but they're always going to be parallel to either the x-axis or the y-axis. And the only thing that really changes then is going to be this radius formula, this r of x that I was kind of alluding to and there just to the side. So what will happen is you end up having to adjust the radius function r of x or r of y accordingly. And it'll help if you draw out the radii in order to pull this off. So let's look at an example. We're rotating a region bounded by y equals 2 minus x squared, y equals 1, about line y equals 1. Okay, so let's get a picture going. 2 minus x squared, so that's a parabola x squared rotated about the x-axis, so it'll be facing downwards, and then shifted up 2 places. Okay. And then it'll go through about 1 point something. No, root 2 is, yeah, 1 point something. Okay. So let's draw that thing. Then the line y equals 1 is right here. And that's the same line we're rotating about. So the region is given by y equals 2 minus x squared and y equals 1. That's that region there. And then we also want to rotate it about the line y equals 1. So we're rotating about this line. Okay. The end result is going to be kind of like a football. Okay. So you get this kind of figure resulting after we spin it about that axis. Maybe it looks like a bit like a Stewie head. Right, so draw the rectangle, okay? The Riemann man is still going to, because we're going on an axis that's parallel to the x-axis, the Riemann man is still going to be kind of running in this direction, okay? The rectangle, the base of the rectangle, if you draw one of the little rectangles, is going to be on the x-axis. So in particular, this guy is at location x sub I with width change in x. So it has variable height as the Riemann man goes across the x-axis. So what is that formula for the radius, which is really just the height of that particular rectangle? Well, it's a difference, right? It's two things. And let me sort of draw, it's this height from the x-axis to the top of that red rectangle minus this height, the distance from the x-axis to the line y equals 1. If you subtract those two, then you get the red height. Right? So that's exactly what you want to put in the radius function. You want the formula that gives you the height of the big rectangle, which is 2 minus x squared, minus then the formula that gives you the height of the smaller rectangle, that second rectangle, which is constant in this case. It's just 1. It's always 1, no matter what x sub I position you're at. You can simplify the formula a little bit. It's just 1 minus x squared then. And then you plop it into your integral. So we get pi times the integral of r squared, so 1 minus x squared dx. And we're integrating from, we're going to need an intersection point where the 1 intersects with 2 minus x squared. So let me get for the intersection point. You're just equating y equals 1 and y equals 2 minus x squared. So you have 2 minus x squared equals 1. I'm going to move the x squared to the right, and same for the 2. So you get x squared minus 1 is 0, so x will end up being plus or minus 1. So those will be the bounds on our integral. You can make it a little easier on yourself by using symmetry. So if you just go from 0 to 1 and multiply it by 2, you should get the value. Okay. So what do we get then? And this has to be squared. Okay. So what do we get? 2 pi times the integral of 1 minus 2x squared plus x to the 4th dx from 0 to 1. That will be 2 pi times x minus 2x cubed over 3 plus x to the 5 over 5, evaluated from 0 to 1. This will be 2 pi times 1 minus 2/3. Let's get a common denominator, right? So it's going to be 5/5. Oh, we're going to have 15 as our common denominator. So 15/15 minus, will end up being 10/15 plus 3/15 minus 0. So 8/15. 2 pi times 8/15 which will end up being 16/15 pi for the volume. Okay. So just keeping track of the radii, using the idea of differences, it's kind of like the donut hole principle, right? You can find the area volume of the donut if you just take the volume of kind of the kind of a circle, figure out the volume of this kind of circular part, and then subtract away the volume of the donut hole, and you get the volume of the donut, right? That's what I mean by donut hole principle. So this is donut without, can't really call it a donut. If a donut doesn't have a hole, then it's not a donut. So anyway, it's just a big thing of, I don't know what. All right, well that's, okay, so let's move on. Section 4, now we introduce the washer method. And the big change here is now you'll have kind of a difference of radii. So you'll have, and this is really that washer idea that I was just talking about. So imagine you want to know the volume of a ball bearing that has a hole in it. Okay, so we have this ball bearing and it has this hole in it, right? So to figure out the volume of that, what you're going to need to do is just find the volume of the ball bearing and then subtract away the volume of the hole. Okay, so that's going to be kind of our idea here. Let's derive it like we did for the disk method. Kind of talk about what all the little objects look like. What did they represent? So here it's the region that we're rotating will kind of be the difference of two regions, right? So let's take a look. Here is one curve. We'll call it f of x. And then we have some other curve, we'll call this guy g of x, and we're rotating this region between the two curves around the x-axis. And what you end up with this time is kind of a goblet with a hole in it, okay, a hole through it. So you can stick your arm in it, basically. And if that happens, you have to use the washer method. Okay, so anyways, you can kind of, imagine sectioning it up into a bunch of little rectangles. And again, the rectangles won't necessarily correspond to the way we traditionally think of them. Like we're not assigning areas to these, right? Instead, it's going to be a volume, and a volume of what? Well, instead of discs, it's going to be washers, basically discs with holes in them, right? So we'll look at in particular at this red rectangle, and what does that thing represent? It represents a washer. Okay, so if you're a mechanic or you work with nuts and screws all day, you know what a washer is. But for us, the washer is basically going to be a smushed cylinder with a hole in it. Okay, so it's going to be this object, and the Riemann man then is running across the x-axis, and of course we could do the y-axis as well, or a non-axis. The Riemann man is running across and picking up all these volumes, which represent volumes of this washer thingamajig. Let me draw in the rectangle. So the rectangle this time should be right here. Okay. And we need to use all these dimensions and formulas in order to get the volume of this resulting thingamajig. So let's take it and reorient it so it looks more like a cylinder that we're used to. Okay. So we have kind of the hole in it, and then this outer part, looks something like this. Right. There's the red rectangle sitting inside of it. And okay, so the volume of this thing now will be the difference of two volumes, right? So it's kind of the volume of the big cylinder kind of, it's the donut hole problem again, right? So I need to figure out the volume of the big guy, which will have kind of one radius. So the radius of the big, so you know, what am I, you're finding the radius of this cylinder, this bigger cylinder, and then you're subtracting away the radius of the hole. You're subtracting away the volume of the hole, and what you end up with is this guy, right? Okay, so this first radius then, what is that? That's what I'm after over here. The first radius from the x-axis is from the x-axis to the curve f of x. Okay, so that first radius is given by f of x sub I. Okay, so this distance from the middle to the outer edge is f of x sub I. Then for the donut hole, that radius is given by what? Well, that's going from 0 to g of x. So that radius is just g of x sub I. Okay, and we can put that in our picture over here, right here. Okay, and then the heights will be your change in x, right? That's just the base of the rectangle. Okay. So, in order to pull off the volume, over here we have the volume is basically the difference of these two volumes. But we can rearrange that and make it a little more usable by factoring out the pi and the change in x, right? We'll end up with pi times f of x sub I minus g of x sub I times change in x, okay? Okay, so ultimately then the Riemann man is running across and adding all these volumes up, and then we go ahead and take the limit as the number of those washers goes to infinity, and we end up with our second integral for the washer, which is pi times the integral going from a to b of f of x minus g of x, and these are both be squared by themselves, so f of x squared minus g of x squared dx. Okay. And the way I usually think of f of x and g of x is like a big radius, I'll call it big R of x, minus a little radius, little r of x, dx. Okay. Clearly, we can worry about x-axis and y-axis rotations. For the y-axis, it will just be a difference of, so for x-axis rotations, you may have some region like this that we're rotating about the x-axis, and then your rectangles and your Riemann man orientation. So we have like an f of x, let's make this g of x, and f of x, and this rectangle is at location x sub I for change in x. If we're going around the x-axis, Riemann man is going like that, and our formula, of course, will end up being pi times the integral of the big radius, which is in this case f of x, squared minus the little radius squared dx from whatever to whatever. But in the other orientation, then if you do y-axis rotation, however you want to do your thingamajig, let's say we have kind of the same curve, except now we're going to have to call them something else, right? So call this h of y, and then this guy's g of y. Our rectangles will be oriented in this way. Okay. So a particular y sub I, and then the width is change in y. Our Riemann man is running up the flagpole like this. Okay. So our integral in that case will end up being pi times the integral from c to the d of our g of y squared minus our h of y squared dy. Okay, okay, great. Well, let's go ahead and then take a look at an example. If I can find one. Okay, so we have this region given by x squared, and then y equals 4x minus x squared. And first we'll do, yeah, sure, we'll do x-axis rotation, okay? So I need to graph these guys. X squared is easy to graph. 4x minus x squared. So let's get the intercepts. So set it equal to 0. Factor out an x. Get 4 minus x. So its intercepts are at 0, and then at 4. Its vertex. To find the vertex, you could take its derivative and get the critical point. So you remember doing that maybe in Calc 1. 4 minus 2x. Set it equal to 0. That gives you the critical value. Because the critical number tells you about maxes and mins. And if you're dealing with a parabola, the in this case, minimum is going to be at the vertex. Okay, so you can find the vertex by just minimizing or maximizing, which comes down to taking the derivative and setting it equal to 0. So you get 2x is 4, so x is 2. And then you can plug that back into the original formula for the y coordinate. So y of 2 is 8 minus 4, which of course is just 4. So our vertex is going to be at 2, 4. You may remember back in college algebra using the formula negative b over 2a comma f of negative b. You get the same answer as if you took the derivative and maximized it. Okay. This is also the vertex formula. Okay. So anyways, you get a pretty good picture. You want to know where these guys intersect. So for the intersection, we'll have x squared equals 4x minus, you just set them equal to each other, right? Then you get 2x squared minus 4x is 0. Factor out 2x, x minus 2 is 0. So it looks like at 0 and then at 2. Okay? So at the vertex and at 0, 0. Okay, so let's get a graph. And here's a picture. So 1, 2, 3, 4. 1, 2, 3, 4. The vertex is at 2, 4. X-intercepts at 0 and 4. So the upside down parabola, the y equals 4x minus x squared, looks like this, more or less. And then y equals x squared is going to hit 0, and then at 2, 4 it hits right there. So it's going to look like this. Right, so the region that we're worried about is this blue region here, and we are rotating it about the x-axis. Okay? So let's get our rectangles. Remember, the rectangles are always perpendicular to the axis of rotation. So there's our rectangle for our particular x sub I. Okay. We'll need a big R of x, a big radius, and then a little radius. Okay. So the big radius is variable. The little radius is also variable. And the base is on the x-axis, so you could tell the heights are going to be functions in terms of x. Okay, as your Riemann man is zipping across, collecting all of these sort of volumes of disks. Okay. Okay. So again, it's kind of, you know, the big radius is from the base to the top. That's this distance for r of x. That distance is given by the upside down parabola, so we can type that in here, 4x minus x squared. Little r of x then is the distance from the x-axis, so we'll do this in yellow, to the base of the red rectangle. So it's basically this distance. That distance is given by the y equals x squared curve. So that will just be little r of x is just going to be x squared. I guess I did that in yellow. Okay. Okay, and then it's just plug and chug. The Running Man is going from 0 to 2 on the x-axis, and then big R of x squared will be 4x minus x squared squared. And then little r of x squared will be x squared squared and dx. And then we just have a little bit of math to do, right? Some integration. Okay, so 4x minus x squared. So we get 16x squared minus 4x cubed minus 4x cubed is 8x cubed plus x to the fourth minus x to the fourth. So that's a nice little cancellation. So that'll be pi times the integral of 16 x squared minus 8x cubed dx. Integrate. So we get the antiderivative as 16x cubed over 3 minus 8x to the fourth over 4, which will be 2x to the fourth. And evaluate it from 0 to 2. So plugging 2 into the antiderivative, I'll have 8 times 16 over 3. 128 over 3 minus 2 times 2 to the fourth. So 32. I want a common denominator of 3, so I'm going to multiply that by 3. So 96 thirds. And then minus 0. You plug 0 into the antiderivative, you just get 0. So 128 minus 96, 2, 0, 3, 32 thirds pi. Okay, and that will be the volume. Okay, one last thing then. Let's look at the washer method with a non-axis revolution. And again, what you're going to be doing is kind of adjusting your big R and little r accordingly. So adjust big R of x and then little r of x based on your rectangles. Okay. So let's look at an example of that. We'll have this, let's just keep with the same picture, so I don't have to go through the trouble of redrawing it. Same functions. 2, 3, 4, 2, 3, 4, 2, 4. We have that one. Y equals x squared. And then this guy. So our region is this. And then we want to revolve it about the line y equals 6 for 3, 4, 5, 6. So we want to rotate it about this line. Okay. So note, if you do rotate it, you're going to end up with an object that has a hole in it, right? It's going to be kind of, I don't know how to describe it, but it'll end up kind of, being like this, where your cross section of the thing is like this. So that thing is rotating out and giving you this kind of picture. So I don't know. It definitely has a hole in it and through the bottom of it. It's a terrible picture, but sorry, that's the best I can do. Let me just get rid of that because it's so nasty. But there's a definite hole in it through the middle. And then if you cut it in half, it would have a cross section like this, little flap, kind of like the cross section of a wing of an aircraft or something, an airfoil. I think that's what they call it. But anyways, the rectangles that you're working with, the Riemann man is going in this direction, collecting these washers. The rectangles that we're working with will be like this. Okay, and then at least we get a picture of one particular washer, I guess. That would be generated from that thing I just drew, that one rectangle. So one particular washer. We have, it looks something like this. So that red rectangle is sitting right in here. Okay. Oops, I accidentally put them a little too high. Yeah. Okay. So the Riemann man is running through collecting this thing. We need a formula for the big radius and then the little radius. Okay. So the big radius I'll do in blue is going from this axis that we're rotating about all the way down to the parabola y equals x squared curve. Okay. So I need a formula that gives me that length. And to get that length, you basically do a difference, right? So I can kind of put it in maybe this weird color here. That rectangle is the difference between this rectangle going from 0 to 6 and the smaller rectangle going from the x-axis to the curve, right? So the big rectangle, again, is constant as the Riemann man runs across the picture. It's just always 6. And then subtracting away the little section, that's going to be variable, and it's dependent on this line y equals x squared, right? That little rectangle I just put in yellow. Let me get rid of it now. Hopefully it's not going to explode and get rid of everything on there. Okay, so then it's minus the x squared. For the little rectangle, then let me get rid of this stuff. For the little radius, that guy, if I do it in blue, is the distance from here to here. Okay? And again, you do it in terms of differences. It's going to be this constant distance throughout, and then you subtract away the distance to the curve itself. Right? In this case, it's weird because the top curve is kind of like the bottom curve, okay, in this orientation. So anyways, it's 6 minus the distance to this, in this case, top curve, which is really the bottom curve in our orientation. So 6 minus whatever that top curve was, 4x minus x squared. Yeah, 4x minus x squared. Okay. And then we can put it on our integral and chug away. So I'm going from 0 to 2 again. Big radius, 6 minus x squared squared, minus little radius, which is 6 minus 4x minus x squared squared dx. We'll just set it up. We won't bore you with the details. Okay. Okay, so that's the idea. There's 2 methods here. There's the disk method, and I forgot to give you a quiz problem. The quiz problem will make we'll make it this example here. So this is also then the quiz. Let me mark that in my notes. So you have to copy out this junk. Please show me the picture, the rectangles, all the little details. Okay, so let me mark it down so I have it in my notes. What you are doing. That's my pencil. 2. Keep forgetting to tell you about the quiz every time. Where am I? Oh, the disk method. I'm just sort of restating everything that we did. So again, there's 2 orientations. But the formulas are basically radius squared, the pi out in front, and then dx, where you just replace all the x with y's, right? And then the washer method, you have 2 radii. So you have bigger radii, and you're kind of figuring out that volume there, and then you're subtracting away out the sort of donut hole radii volume. Okay. And then that's one big So those are the two formulas, and then of course you need the y orientations, but hopefully that will get you through the problems and the homework. Okay, so thank you for watching, and we will see you next time.